Imagine Earth has a cousin. A cosmic cousin. Living in a different stellar neighborhood. Circling a different parent star. This isn't science fiction. In 2015, astronomers using NASA's Kepler space telescope announced they had found just such a world. They named it Kepler 452b. The discovery sent a ripple of excitement across the globe. Not just another planet. The most Earth-like exoplanet found at the time. A second Earth, Earth 2.0, captured our collective imagination. It made us look up at the night sky, wonder about points of light, and the possibility of other worlds that feel like home. It orbits a star much like our sun, and sits in a region where liquid water could exist. That fact is profound. For millennia, we've asked, are we alone? Kepler 452b doesn't answer that, but it offers a powerful hint. It implies Earth-like ingredients aren't unique to our corner of the Milky Way. The universe knows how to build worlds like ours. So, how do you find a planet that is 1,400 light-years away? You can't just point a telescope and take a picture. The planet is far too small and dim, completely lost in the glare of its parent star. Instead, scientists used a clever and patient technique called the transit method. The Kepler Space Telescope was designed for this very purpose. It stared, unblinking, at a single patch of the sky containing over 150,000 stars. It was a cosmic census taker, meticulously measuring the brightness of each and every one of those stars, day after day, year after year. The transit method works like this. If a planet's orbit is aligned just right from our point of view, it will periodically pass in front of its star. When it does, it blocks a tiny fraction of the star's light, causing a slight, temporary dip in its brightness. Think of it like a gnat flying in front of a distant, powerful searchlight. You don't see the gnat itself, but you can detect the momentary shadow it casts. This dip in starlight is the telltale signature of a transiting planet. It's a subtle effect, often a change in brightness of less than 1/100%. Once astronomers confirmed Kepler 452b's existence, the next question was, what is it like? The transit data gave us our first major clue: its size. Kepler 452b is about 60% larger in diameter than Earth. That puts it in the super-Earth category. We have no examples like this in our own solar system. Larger than Earth, smaller than the ice giants, Uranus, Neptune. Their presence forces us to rethink what a planet can be. Size matters. Astronomers think it could be rocky, like Earth, like Venus, like Mars. Planets this size are more likely to have a solid surface, versus being a mini Neptune, a small core with a thick, crushing gas envelope. Imagine standing there. Gravity might be about twice Earth's. You would feel heavier. Landscapes could be shaped by stronger gravity. But we must be clear. We only know size, not mass. Without mass, we can't calculate density. And density is the key to composition. Kepler 452b completes one orbit in about 385 Earth days. One of the most exciting things about Kepler 452b is its location. It orbits within its star's habitable zone. This term, sometimes called the Goldilocks zone. The habitable zone is the region around a star where the temperature is just right. Not too hot, not too cold, so liquid water can exist on a planet's surface. On Earth, where there's liquid water, there's life. So the habitable zone is the first place we look for life as we know it. Kepler 452b's star is a G-type, the same class as our Sun. It's a bit older, about 6 billion years old. The star is about 10% larger and 20% brighter. A brighter star pushes the habitable zone slightly farther out. Kepler 452b orbits just a little farther than Earth's orbit, placing it squarely in that temperate zone. It gets about 10% more energy than Earth does today, making it a slightly warmer cousin. That Goldilocks idea is powerful, but there are important caveats. Being in the habitable zone doesn't guarantee habitability. A planet also needs the right atmosphere to keep a stable surface temperature. Venus, baked by a runaway greenhouse. Mars, a frozen desert under a thin sky. So Kepler 452b needs more than the right address. The story of Kepler 452b is as much about what we don't know as what we do. The vast distance, 1,400 light-years, is a profound barrier. A light-year is the distance light travels in a year, which is nearly 6 trillion miles. To travel there with our fastest current spacecraft would take tens of millions of years. All our knowledge is indirect, gleaned from faint signals that cross this immense cosmic ocean. We have a few tantalizing data points, but the full picture remains shrouded in mystery. We are like detectives with a few clues, but no eyewitnesses. One of the biggest unknowns is the planet's atmosphere. Does it have one? If so, what is it made of? It matters because it acts as a mirror. In its reflection, we see the possibility of ourselves, a planet of a similar size, with a similar length year, orbiting a similar star. It validates a deep-seated human hope, that we are not a cosmic accident. It gives missions like the James Webb Space Telescope a clear purpose, to move beyond simply detecting planets to characterizing them. We want to search for the chemical fingerprints of life: oxygen, methane, water vapor. The search continues, and Kepler 452b beckons us forward, urging us to keep looking up, and to keep wondering.